So in our last presentation, we talked about stacks. And in stacks, the insertions and deletions both occur at the top of the data structure, or the front. Queues are a little bit different. Insertions take place at the rear of the queue, and the deletions or the removals take place from the front of the queue. If it's more comfortable for you, you can think of the American term line, and that might make it a little bit easier to understand what's going on. So queues are first in, first out data structures, or FIFO. The elements get added to the back, and we remove the elements from the front. You can implement a queue in the same ways that we implement a stack, but we also need an additional pointer called the back pointer. That's in addition to the front, which works like the top pointer in the stack, or the head in the linked list. So let's look at the first way, which is making a queue using an array. This is kind of the old school way, the way I learned back in the 1980s. Since we now do a lot of work with dynamic memory, it's a little bit easier to make them with pointers, but let's talk about making them with an array. So we have the array that stores the elements. We have a pointer to the queue front and one to the queue rear. These are used to track the first item in the queue and the last item in the queue. And also need to keep track of the maximum size of the queue in order to avoid overflow or underflow conditions. So if we keep track of the current size and the maximum size, we can prevent too much from going in, or from having a situation where there's nothing in the queue and we try to take something out of the queue. So adding an element, basically we advance queue rear to the next position. So queue front here is at A, and then queue rear is at 2, which is element C. We want to add a new element, which is D. We advance queue rear to the next array position, and then say that queue rear is equal to D, and that would add D to our queue. Deleting an element, we retrieve the element using the queue front. Here we would get queue front, and that would give us A, and then we advance it 1. We don't need to worry about the deletion or the reallocating the memory in this case. So problems with the array implementation: one, it can overflow at the rear due to several insertions and deletions, because remember, we're advancing that when we move things off the front. We're going forward one, and we can end up going past the rear, particularly if we have several insertions and deletions that take place throughout the lifetime of the program. One solution is to check the value of the queue front. If it indicates there's room in the front of the array, slide all the elements over to the first array position. That does take a lot of shuffling, but it is a solution. Or solution 2, you can use your friend the modulus operator and a circular queue. So you basically end up at in this case, the front of the element would be 98 and the rear would be position 0. So it kind of reverses the front and the rear, but we can use modular arithmetic to accomplish that. Another one is if queue front and queue rear are identical, that means that basically they point at the same thing. It usually means we have an empty queue, but not always, because it could be that, hey, there are more elements in there than we need. And basically keep a count, increment that count when a new element is added, and decrement it when an element is removed. Initially set it to 0 so that there are 0 elements in the queue. And this is also useful if a user of the queue needs to know the number of elements in the queue. So it gives us additional information, and it's not a bad thing to add in, particularly if it's a class. Just have another attribute to that class. And solution number 2 is let queue front indicate the index of the array position preceding the first element, so that you don't end up with those two being equal. So we can also make a queue using linked lists, and this is probably the easier implementation. It avoids some problems. The queue never gets full since memory is dynamically added as needed, and we're also not using more memory than we necessarily need. We could run out of memory if we allocate too much or forget to clean up the dynamic memory, but those are problems that we've solved in previous lectures. Need only 2 pointers to maintain the queue, the front and the rear, and it's easy to determine if the queue is empty. And in fact, this is the initialization condition: front is equal to null, or front is equal to null pointer. So head is the front of a linked list, and for queues, we're going to use front as our pointer. We use back to indicate the other end where we're doing the insertions. The constructor is basically set front and back both equal to null. Copy constructor, again, we would use a for loop to go through and make a copy of the queue item by item so that we get every item in the queue. To add items to a queue, if there's an empty queue, then we add a new item to the front and set back equal to front. For a non-empty queue, we need a temporary node pointer for the new queue node. We set back to link to the new node and update back to point at the new node. And it's just like linked lists, it's important to get those things in the right order, or else you can run into problems with memory leaks. Removing items from a queue. If it's an empty queue, well, you can't really remove anything from an empty queue. So this should have an error condition. Otherwise, make a discard pointer and have it point to the front, then change the front to point to the next in line. And that can be front is equal to front followed blank. And then check to see if that's null and delete our discard pointer. So, there are some conditions in there for inserting items. So, a lot of different applications. It can be used in different types of search, but one of the better applications is actually modeling with queues. And Malik actually covers this in his text, which is one of the things I really like about this particular text. And there's a whole field of queuing theory that can give you good predictions on how long you'll wait in line. This is used like if you call a busy company, like a cable company, they'll give you an estimate as to how long you might be on hold with them, and the option to call them back. So modeling with queues is tremendously useful. Disney uses this as well in order to predict how long that you might be in line for a ride at one of their theme parks. So with queues, there's different options to model, and one of them is simulation, which is a technique where one system models the behavior of another. And computer models, we often use them to study the behavior of real systems. Queuing systems, we can make computer simulations using the queues as data structures. And basically queues of objects that are waiting to be served. So if you think about one of the drive-throughs for the fast food places in town, or waiting in line at KTA or Island Naturals in order to check out, then that's a queue. And we'd like to know how long it takes, or to get a good estimate on it. And Malik actually does go through and show how to do this in C++. You can also do this using mathematical equations, and the type of model you choose for the queue depends on how the processes or the customers arrive and how the system provides service to them. The simplest type of queue is the Markov 1 model, where there is one queue and both the inner arrival times and service times are exponentially distributed. So basically they follow that negative exponential slope on a curve. In order to model such a queue, you only need to know the arrival rate and the service rate. And from these, you can calculate rho, or the traffic intensity, which is equal to the arrival rate divided by the service rate. If rho is less than 1, basically we have fewer arrivals than we have the capacity to serve. We can serve more people than are arriving, then the system is stable. And like anything where you get more people arriving than you can actually deal with, the system becomes unstable, and you lose customers from line, or things shut down, or people get upset or angry. So you do want rho less than 1 to mean the system is stable. At certain points in time, it might not be stable. You might get more arrivals than you can deal with, in which case the queue grows. But eventually you want that queue to shrink so that you're always having things come into the queue and go out of the queue. You can calculate the mean response time. That's 1 over mu divided by 1 minus rho, and the variance of the response time, which is given by the equation 1 over mu squared divided by 1 minus rho, the quantity squared. Other calculations, you can get the probability that there are n jobs for any n. So what's the probability we'll have 3 people waiting in line? Mean number of jobs in the system, how many can we expect on average to be in the system at a time? The variance of the number of jobs in the system, the mean number of jobs in the queue, that is the ones that are not being served, and the variance of the number in the queue. So how much does that quantity vary? You can calculate the mean waiting time, and this is what they do when they determine how long you're going to be on hold, or when Disney says from this point there's a 15-minute wait to get on the ride. And you can also calculate the variance of the waiting time. Lastly, and this is important, you can calculate the utilization, how busy the system is. You don't want the system to be 100% busy, in a company that's going to burn people out, or in a machine that's going to kind of overheat the machine, but you don't want it to be zero either. So utilization is kind of one of those nominal is best type metrics. And there are a lot of other calculations you can do. In fact, if you want to take a look at this, Raj Jain has a great textbook on the subject, and it can show you all the different calculations. So, consider a server that has 125 requests per second coming in, but it can deal with 500 requests per second in terms of its capabilities. Well, the arrivals are 125 per second, and the service time is 500 per second. From here, we can calculate the utilization. That's 25, and the mean number of jobs is 0.33, and the mean time they'll spend in the system is 2.66. Other types of queues, there are general ones which don't give you as much specific information as the Markov queues, and there's Erlang queues and several different types of different queues. And again, that Raj Jain text is a wealth of information on this. So next time we'll have a lab and we're going to play with this stuff, and from there we're going to explore the standard template library. Thanks as always for watching.